Hi everyone, I'm Haley Bowden from the University of Arizona. I'm a graduate student working with Peter Baruzzi. And I am going to talk to you today about what information we can get from the galaxy environment about halo properties. So I'm first going to start with just like a general trying to disentangle this question of what can we learn about the properties of dark matter halos from their observable environments with machine learning. And it's kind of broken up into a few parts of why do we think that there's information in the environment? What kind of information is in the environment? And then how do we best extract that information? I forgot to use this. Okay, here we go, cool. So then I'll just be going over an overview of the project I've been working on for a couple of years now, trying to estimate the halo masses from the Bulltride simulations. Then I'm going to go briefly into how we've been trying to open the box on this neural network and determine what information is important and how the and how we might determine if the network is robust. And finally, an overview of our plans moving forward. So to start off with, why do we think that there's information in the environment? So there has been a lot of work on this, and I'm going to specifically focus on this one paper by Baruzzi here in Moster in 2021, that, and in particular this figure, we're looking at the probability of a large value for one of these halo properties versus over a probability of a small value as a function of the environment, which in this case is measured as the distance to the fifth nearest neighbor. And so by plotting these relationships, we can see that each of these halo properties has its own relationship with this measure of the environment, this distance to the fifth nearest neighbor. And in a particularly exciting note to everyone here that cares about galaxies, we can then use this relationship and then go and look at the properties of galaxies, for example, galaxy size, and see how they correlate with the environment. And in comparing these relationships, we can see, we can test different models of connections between galaxies and halos. So in this case, this is looking at the two-point correlation function of projected distance. So there are a lot of different ways that we can measure the environment, though, and there's a lot of different information there. So one of the things that we've been talking about at this workshop conference is having these like high-dimensional, having high-dimensional data, like having an image of a galaxy, and then how do we put that into a piece of information that we can actually use, like a summary statistic. And so we don't necessarily know that the distance to the fifth nearest neighbor or the two-point correlation is the best number to relate our halo properties to the environment. So what I'm looking at doing is using a neural network to find that relationship instead. So first, I want to give it as much information as possible from the environment. So there's two kind of ways that I can define this information. And one of them is with a fixed number of neighbors. So this would be kind of over a variable distance scale. So I can take a target galaxy and take a redshift slice around it and say, what is the distance to the nth nearest neighbor? And I can even make a list of that, list of those from like first to fifth to 10th. So that's one way I could describe the environment. Another way I could do it is to take a target galaxy and define a fixed distance away from it, projected distance, and then just count all of the galaxies that are inside of that. So fixed number of neighbors, fixed distance. For the rest of the talk, I'm going to be focusing on this one, but I think they're both interesting things to consider. So in terms of the network, I'm trying to do something relatively simple as it comes to neural networks, where I just take a big vector of all of the distances to galaxies, in this case 50 nearest neighbors, and the stellar masses of all of those neighbors. Goes through some fully connected hidden layers, does its stuff, and outputs one value, which is this halo property. And looking primarily at halo mass. So for halo mass, we've seen that there's a strong correlation between stellar mass and halo mass. That gives us a pretty strong predictor of what a galaxy's halo mass is. However, there's scatter in this, and some of it is explainable due to the okay. There's scatter in this relationship, and especially at a fixed stellar mass, when we go to the higher mass end, we can have a much broader range of possible halo masses. And one of the ways around this, if we want to have an accurate halo mass, is to use, for example, the satellites of the galaxy. We can use the dynamics of that system to then get the halo mass of this group in like cluster scale end. And potentially, maybe we can go beyond the satellites. Maybe there's information in the 2 halo term, that kind of thing. But there's definitely information there in the environment. So just to get some intuition in terms of what we might expect the network to be using for different halo masses, we can look at the projected distance to the nth nearest neighbor as a function of the peak halo mass. And depending on the shape of each of these distributions, we can kind of predict, get some intuition for where there's information and where there isn't. So for example, if we look at the 50th nearest neighbor, this region is pretty flat, so we wouldn't expect it to perhaps use this information to be particularly important for, say, distinguishing a halo at 10 to the 12 solar masses versus a halo at 10 to the 12.5. Whereas if we go to a more sloped portion, we might expect that to contain more useful information. So then we can look at what the network actually does. You can see that by far the majority of our galaxies are in this little sample here. So I've trained the network on the small multi-dark Planck simulation, SMDPL, and which is and then tested it on a slightly smaller box, which is the Bolshoi-Planck simulation. So this is the results on the Bolshoi-Planck simulation. And yes, so in this region where most of my galaxies, most of our halos fall, this is performing pretty well. If we go to higher halo masses, you can see that performance is, the scatter starts to get a bit larger, but it still is performing quite a bit better than when we compare it to a prediction from stellar mass alone, which is what I'm going to do now. In black, we have the stellar mass alone, a prediction of the halo mass. And then we can add different amounts of information from the neighbor density distribution. And we can ask a lot of different questions. So one of them is, how does the error in our prediction depend on halo mass? Okay, as expected, it's going to increase as we go to higher halo mass. But if we add more neighbors, especially if we add past 5 neighbors in this case, we can get a lower error in our prediction of halo mass. Now, this is a network that was trained to equally weight all of the training data. And our training data happens to be very biased to have a lot of galaxies in this end, so it doesn't care about this end very much. But if our science goal is to look at this end, then we could see that, okay, we're not improving too much on the stellar mass-halo mass relationship in this regime. So there's not too much extra information being gained there. We have basically, basically at the bottom here, some intrinsic scatter that is introduced from our errors and observed stellar mass, that kind of thing. But if we weight the higher mass neighbors higher, because we care about those more for some reason in this case, then we can see that including more information is going to reduce our errors at higher halo mass. So how we weight our training data, or like what loss function that we choose for our training, is going to impact the performance of our network in these different regimes. So yes, that is mostly what I want to talk about in halo mass, and then just to give a sense of why we're doing this and where we're trying to go with it. I have these plots are also made from the data from that Baruzzi Moster here in 2021 paper, looking at the small versus large growth rate as from 2-point correlation versus the distance to its nearest neighbor. So we're very interested in looking at halo properties beyond halo mass. So looking at angular momentum, looking at concentration, at growth rate, that kind of thing. And our general strategy looks something like this. We start with our galaxy stellar masses being from universe machine. Then we train a neural network with our environment as our input and some halo property A as our output, like we've done for halo mass. Then we do what we need to do, and I'm open to lots of suggestions for this, in terms of making this network robust so we can apply it to observations. And if we apply it to a large observational survey, then we can make a plot just like the one that I showed towards the beginning with galaxy size and halo growth rate. We can make this plot of galaxy property versus halo property, or how both the galaxy property and the halo property evolve with the environment, and look for correlations there. And that'll tell us for our future simulations what kind of relationship we need to be able to reproduce. So that's an overview of where we're at, where we stand. That's not. So we're working to develop networks to summarize the information in the environment in ways that are sensitive to these different halo properties. So it's sensitive to predict halo mass, to predict halo concentration, and so on. We currently have a network that can accurately estimate halo mass for over a wide range of masses for the Bolshoi-Planck simulation. We found that depending on which mass regime we're working in, or that we care about, varying the number of neighbors that we could include and just, the loss function that we use is really important for the results that our network ends up giving. And then looking forward, training the network on different halo properties will be one of our main focuses, along with figuring out how to apply these networks to observational surveys in the best way possible. That is all. Thank you very much.
Thank you so much, Haley. Do we have any questions? All right, I guess. Yeah, Louise, you can go first.
Thanks, Haley. This is Louise Edwards. Why did you pick 50 as the number to explore? And then can you give me an idea of what distance that is if I'm in like a rich cluster or something like that?
Yeah, so go back to. So 50, because for the most part, this relationship is it gets getting flatter and flatter as we go out to a higher, but there isn't necessarily a perfect cutoff that we know. So 50 is the number that I chose. It is definitely worth considering if, as I'm examining removing features, if it turns out that 50 is the best performing of versus 25 neighbors, then maybe it's worth considering further out. But yes, for now, it seems like there's not much information to be gained, at least as the network is set up now, from neighbors beyond 50, and we're going out to about 2 to 3 megaparsecs.
All right, yeah. So let's go, John, now.
Hi, John Wu. Thanks, Haley, for a great talk. So is your method applied only to central galaxies and subhalos? And if so, do you think there's any hope of doing so for satellites?
Yes, okay, thank you. So my method is actually, I'm looking at both centrals and satellites. So let's see, okay. And so, you know, at the low mass end, we have predominantly satellites here, and that I think is why, well, partially along with some selection effects is why our performance is here. So if we look at, say, light blue is this light blue one here is centrals. This dashed is all of them, and then this green is satellites. You can see that our overall performance is much better for centrals, but that there is some prediction power for satellites.
Oh, and just to clarify, the halo then is that of the subhalo then if it's a satellite?
Yes,
okay,
yes, sorry,
great.
subhalos.
Thanks. Yep.
All right. Thanks for the great talk. Hao Zhang speaking here. So could you go back to the slide where you showed the prediction error versus halo mass? Yeah, right here. Yeah, okay. So firstly, in this like low mass regime, this prediction error is not a monotonic function of halo mass. So do you understand why that is?
Yes, so a big portion of this is the fact that I am selecting only galaxies over with stellar masses 10 to the 9 and greater. And so I'm preferentially, of the halos with in this mass range, I'm preferentially selecting the ones that have overly high stellar masses. Yes, that is I think the predominant reason that is happening.
Okay, thanks.
Paco, yeah.
So very nice talk. I have a technical question. So when you change the number of neighbors, do you change the architecture or you keep it the same?
No, so currently the way that I'm changing the number of neighbors is I'm just like applying a mask to the input layer. So the rest of the architecture stays exactly the same. I'm just setting like all those stellar masses and distances to 0 basically beyond that.
Thank you. Yeah, really, really nice. So I have quite a few questions, but I will try and just, I think, merge them into one, which is, so, well, at least at the low mass end, if you've got like a 10 to the 9 galaxy in a 10 to the 10 point something halo, it's probably not going to be a satellite. I mean, you're not selecting satellites there, right, and stuff? Because then you're going to have a more massive central.
Yeah, so basically below 10 to the 11, these are almost all satellites. This blue dashed line is the fraction of satellites.
Okay. I don't necessarily understand how that is, but that's okay, because really my proper question is following on from John on this high mass end here. I guess if you maybe it's not so surprising that you don't that you have like a larger RMSE for the satellites, because if you plunge a subhalo into a cluster, basically, then you get all sorts of stripping of the dark matter, and you start like removing that connection that your machine is learning between the number of neighbors and so on.
Yes, I think that is a good explanation.
Okay.
As good of an explanation of that as I have.
Okay, yeah, I think it looks fine to me.
I think, Matt, you have a question? Or?
No. I'll do my job.
Thanks. Yeah, so I mean, my question was a little bit answered by your answer previously, but with your architecture, when you're including, let's say, the the closest subhalos, in that case, is there a particular ordering associated with the inputs to your dense neural network? And if so, or if not, like, have you tried changing that ordering to see if your model could be robust to switching them around?
Yes, good question. So they are ordered in order of distance. And I have not tried switching them around. That is an interesting suggestion.
Yeah, I think it'd be fine to keep them ordered, particularly because you will always have an ordering. Like, there's hardly ever a case in which you wouldn't have an ordering, but it'd be interesting to try.
All right, any other questions? Otherwise, Sujata?
Oh, I guess here, wait, sorry, I had one more thought on that last question.
All
Just,
right. You get to answer that and then Sujata can
yes.
answer that.
So I guess that there is like already, there's not necessarily an ordering in the association between the distances and the stellar masses, but in giving it the distances, I feel like it is already getting the ordering just by, yeah.
Right. So two questions. One is about the fixed distance. Have you done any analysis on that?
Yes. So I was, let's see, okay. I don't think I have that on here. Okay, so on the fixed fixed distances, so I've considered between like the smallest radius of like 0.5 megaparsecs and then out to 5, with the idea that that would, especially with that 5 then, or that the 5 megaparsec cylinder, that I would get a better constraint on some of those higher mass halos where there are a lot more than 50 close neighbors. I have found so far that the performance seems quite similar to what I get from using the distances to the 50 nearest neighbors. There hasn't been a substantial difference between the two at the moment. I think the as of right now, the 50 or like the distances to the nearest neighbors is performing slightly better at the high mass end actually, but that's very preliminary. I'm still trying to figure out exactly what's the best way to optimize that network with the cylinder counts.
Thanks. So the next question I have is, if you just have some sort of average distance of the 50 nearest neighbors and just try to predict halo mass, how well would you do? And by including all the phase space information, how much do you improve on that?
Okay. I guess the closest to like a summary statistic of of that information I have is including, I've tried doing it with just the stellar mass and the distance to the center of mass of the 50 objects. So that's somewhat of a summary of that system. And that works it doesn't work too much better than the stellar mass alone, as I've had it right now. hopefully separating some of the centrals from the satellites. And so you get kind of a slight improvement on this single stellar mass function versus, not stellar mass function, like a stellar mass halo mass relationship. And instead you have like two separate ones. So that works slightly better at the extremes, but not, yeah, I'll have to talk to you about the comparison of the two, how they line up exactly.
Sure. So we're almost done with question time, but I do have one quick question I just want to ask. So I know that Paco and the other Pablo have tried to do this, but with GNNs. What would you say is the biggest advantage of doing this your way instead of using a GNN?
Yeah, good question. So, I mean, for the most part, I would just say that this is a different way than doing it in the GNN, and that it's probably important to explore multiple methods, just because we don't necessarily know that the GNN will perform better on this information. So with just having this, feature vector, we get like a good comparison point between like how much information would be added by, or improvement would be added by having a graph versus a deep neural network, and yeah, I think that's where I'm at.
Okay. All right, thank you.
Paco,
This might be a little bit weird, but I just want to say that, if you fix the number of neighbors, I think fully connected layers, you are, you are protected by the universal approximation theorem, whereas with GNNs we are not. So GNNs are very good if you have different number of neighbors, but if you always have 50 neighbors or 20, I think in principle this could give you better results.
Sure. Yeah, I would tend to agree. All right, but I think that's most of our time if nobody else has questions. And thank you again, Haley.
Thank you, everyone.